Hello everyone. In this episode, I want to talk about the homomorphism, isomorphism, and the kernel. At first, let's look at the definition for homomorphism. This is the definition for the homomorphism. It says that if we have two groups, one is the group G with star operation, second is group H with diamond operation, then a map phi from the group G to group H which has the following property, that for any x and y in the group G, it satisfies the equality like this: phi x star y equals to phi x diamond phi y. And the left hand side of this equality is you map the result of the operation, the star operation between x and y to h. The right hand side is you do the operation, the diamond operation in the group H for the image of the elements x and y in H. They are the same. Then we call this map phi the homomorphism. The most important thing is this equality we need the map to satisfy, and the idea of this map is that on the left you map the result of the operation of x, y to h. The right hand side you do the map first, then do the operation, then the results are the same. So it means no matter if you do the operation in the first group at the first, then map it to the second group, or you map the elements from the first group to the second group, then do the operation in the second group, the result is the same. So simply speaking, no matter you do the operation first or the mapping first, the result is the same. So this is the idea of homomorphism. Now let's look at an example. So for example, if there is a map between the groups integer group under addition, the map from this group to itself, and the map is defined by for any elements x, it maps to 2x. Then this is the homomorphism, and the meaning of this group, this map is like this. For example, if we consider f maps integer 3 from this group, it will equals to 2 times 3 and equals to 6. 6 is in the integer group as well. So this is how does the map is defined, and we want to show this map is a homomorphism between those two groups. And to show that, we need to show that this map satisfies this property in the definition. So it means that for the left hand side, it is first we want to get two elements x and y in the group integer under addition. Then f is the map, which is same as the phi in the definition. So if we do the f apply to x plus y, what we can get is 2 times x plus y, because the definition of the map. This is equal to 2x plus 2y, and then this is also equals to, because 2x, what is 2x? According to the definition, it is the image of x. so this is fx. Similarly, 2y is the image of y after f, so this is just equal to fx plus fy, like this. And this, so this, we just get f x plus y is equal to fx plus fy. And this equality is just as the same as what we require for the homomorphism. Just you change the star operation and the diamond operation by addition, so they are the same. So this means that this is a homomorphism. Okay. Then after we know what is homomorphism, we can define what is isomorphism. The idea of isomorphism is very simple. The definition is here. It says that a map phi from the group G to H is called an isomorphism if it satisfies those two properties. First property is that the phi is a homomorphism, and the second property is that the phi is a bijection. So simply speaking, the isomorphism is the bijective homomorphism. So this is isomorphism, and we can call, like, if G and H are there is isomorphism between them, then we can call them isomorphic. So isomorphic, and then also we can call them of the same isomorphism type, and we can write them like this: G equals to H under this tilde equality. And like from this notation, we can say that the isomorphism is something, some idea similar to equality. That is true because the idea of isomorphism is that the two groups will behave exactly the same, and that is because because the isomorphism satisfies the property that first it is a homomorphism, so it means that the operation in the group G and the operation in the group H just behave the same, and because the isomorphism is also a bijection, so it means those two groups G and H are just equivalent to each other. The only difference are the notations or symbols you are using for the elements. So intuitively, you can say that if two groups are isomorphic, then those two groups are the same, and the only difference is the notation for the elements and the operation. So this is the idea of isomorphism. And let's look at some examples. The first example is the most simple, the simplest isomorphism, or simplest map, which is isomorphism between groups. That is the identity map. So identity map. So identity map is a map a group maybe G to itself by for any x in the G to the x itself. So for example, if the G group G is a set of four elements, 1, 2, 3, 4, and it will map to itself 1, 2, 3, 4 by the bijection. So 1 will map to 1, 2 will map to 2, 3, 2, 3, 4 to 4. This is the identity map, and this f is isomorphism. So this is the first example, and the second example is exponential map. Exponential map. So exponential map is a map from the group of real numbers under addition to the group of real numbers, the positive real numbers under multiplication, and it is divided by, for any real number, it is mapped to e to x. So this map, this is isomorphism. We can prove this. So to prove this, we need this map f to satisfy those two properties. So for the first property, f should be homomorphism. So for any x and y in the real number, maybe in a group like this, then f x, because the operation is addition in the first group, so like this, it will map this to, according to the definition of f, it will map to e to x plus y, like this. And this e to x plus y is equals to e to x times e to y. And then, because e to x is mapped from x, so this is fx, and the e to y, according to the definition, it is mapped from y, so it is fy. So we get fx plus y equals to fx fy. Because for the first group, this group, the operation is addition, and for the second group, the operation is multiplication. So here is the multiplication on the right hand side. So this is just the definition for the homomorphism. So this means f is a homomorphism. Then we want to show that this map is a bijection. To show it is bijection, we can show it is 1 to 1, 1 to 1, and on 2. On 2. To show this map is 1 to 1, we can see that like if fx equals to fy, then we want to show x should be equal to y. So this will give us ex, because fx is equal to ex equals to ey, and this will give us, if we divide ey on both sides, we will get ex, then divide ey equals to 1, and this is just equal to ex minus y equals 1. 1 is just e to 0, and then we can say that the only possibility when something like e to something is equal to e to 0 is when the power is 0. So this will show that x minus 1 equals to 0, and then then it means x equals to y, which means this map is 1 to 1. So 1 to 1. Okay, this. Second, show the map is onto. It means that for any maybe ex in the group or greater than 0 multiplication in the second group, obviously we have x in the first group such that f(x) equals to ex. So this means the map f is onto, and because this map is 1 to 1 and onto, so it is bijection, and because it is both bijection and homomorphism, so the map is isomorphism. So isomorphism. Okay, so this is the idea for the isomorphism between two groups. Then we can look at the idea of kernel. This is the definition for the kernels. It means that if we have two groups, G and H, and the map phi is a homomorphism between G and H, then we define the kernel for this homomorphism phi to be this set, the set of elements G from the group big G, in which the phi maps those elements G to the identity element of H. This 1H means the identity element of H. Identity element in H. Okay, so intuitively it means that if we have G is here, H is here, those are two groups, and the map phi is here, then for the identity element in H, we call it 1H. Sometimes we might have a bunch of elements in the group G, which is mapped to this one element identity element in the group H, and this subset of the group G is called the kernel of this map. Okay, so let's look at some examples. For example, the first example, maybe we can look at the map in the beginning. This map map the integers under addition to itself by f maps x to 2x like this. So we have proved that this is a homomorphism, so we can check what is the kernel of this homomorphism. To find the kernels, we can check the elements in H by in the first group by the property in this definition. So we want to find all x in Z plus such that fx is equal to 1h if this is called H, and because 1h is the identity element of this group H, and this group is the group of integer on the addition, so the identity of this group is actually the integer 0. So this is 0. So so now the question becomes what elements in this integer on the addition group is mapped to 0 under this F homomorphism, and here, because fx is equal to 2x according to the definition of the map, and we want this result to be 0 because of here, then we have this equality, and the only way we can get 0 by this 2x is that the x is 0. if x is not 0, 2x cannot be 0 for any integer x. So the only element maps to 0 should be 0 itself. So it means that the kernel of f, we write it like this, is the set of one element, and the only element in this kernel is the 0 integer. And so this is the kernel for this example, and let's look at another example. Let's look at the map from the group Z4 to group Z2 by f maps x to x mod 2. Okay, here Z4 and Z2 are the cyclic groups. They are the notation for the cyclic groups, or they can be considered as the group of maybe like this for Zn, for some n integer greater than 0, then this Zn is a set of n elements, and it is a cyclic group of n elements, and the idea for this is the elements in this group are the elements in modular n. So it means, for example, for Z4, Z4 contains the elements 1, 2, 3, not 1, 2, 3, sorry, just 0, 1, 2, and 3, and it is under the addition of mod 4, and mod 4 addition on the mod 4 means that if x mod 4y, it is equal to x plus y with the normal addition, then mod 4. For example, if we have 3 plus 2 under this mod 4 addition, it is equal to 3 plus 2 mod 4. 3 plus 4 is 5, and the 5 mod 4, and the 5 mod 4 means it is equal to 1 mod 4, and that is because 5 equals to 1 times 4 plus 1, and the remainder is 1, so here it is equal to 1 mod 4. So this is a modular operation, which any element, any integer is equal to the remainder when you divide this modulo. Okay, so this is the idea for the modular operation. Okay, and then we say that x is mapped to x mod 2 here. So this is the homomorphism, and you can check it by yourself, and then we can show that this the kernel, what is the kernel for this homomorphism. So because at first let's look at Z2. What is the identity for the Z2? Identity for Z2 is the 0 mod 2 is the identity for this one, and we can just ignore this mod 2 notation. We just say it's 0. 0 is the identity in Z2. Okay, then we want to say what element in Z4 is mapped to 0. So fx equals to 0 mod 2. Okay, and we can check the elements of Z4 one by one. So at first we can see this 0 in the Z4, it will map to 0 mod 2. So we immediately get the identity in Z2. So 0 is in kernel. So as a kernel f equals 0. Okay. How about the 1 here from the Z4, then map to 1 mod 2. 1 mod 2 is just does not equal to 0 mod 2, so it's not in the kernel. But the 2 maps to 2 mod 2, and 2 mod 2 is just equal to 0 mod 2, because 2 equals to 1 times 2 plus 0. So like 2 divided 2, the remainder is 0. So 2 mod 2 is equal to 0 mod 2. So this is in the kernel too. And the last element in the Z4 is 3. Then 3 mod 2. And the 3 mod 2, because 3 equals to 1 times 2 plus 1. So the remainder is plus 1. The remainder is 1. So this equals to 1 mod 2. So 1 mod 2 is not equal to 0 mod 2. So this is not in kernel. So the element 0 and 2 are the only two elements in the kernel. So we get the kernel for this group. And it also shows that the kernel, as we see here, is a subset of G. It can be a lot of elements, not just the one element. But one thing we can say that the identity element, in which 0 for the Z4, and this 0 for the integer under addition group, they are the identity elements in the pre-image group. So the pre-image group Z4 and this integer under addition, they are always in the kernel. So this is one important idea for the kernel. The identity element in the first group G is always in the kernel. And okay. And then this is the idea for the kernel. Then after we know this, we can have a property that the isomorphism is a homomorphism with trivial kernel. Trivial kernel means the kernel only has has one element, and the only one element is the identity element in the group G. So it means kernel F equals to the identity element 1G, like this. And so this property shows the relationship between the isomorphism and the homomorphism, and it also tells us that the isomorphism is a special type of homomorphism. We will talk about this in the future episodes, but here you can just know this property, and if you want to try to prove it by yourself, it is not too complex, but I will not prove here. But the idea is that if the kernel is the trivial kernel, then it guarantees that the map between the two groups is like a one-to-one map. So after it, after we know it is a one-to-one map, and we restrict the image of the map, we will get an onto map. Then we get a bijection between the two groups. So that is the idea how you can prove the homomorphism is a bijection, then the homomorphism is the isomorphism. Okay, and one last thing is that we have defined the homomorphism, and one important property for homomorphism is that the identity. So for any homomorphism F, it will always map the identity of the group G to the identity element of the group H. So this is a very important property for homomorphism, and we can prove that prove this here. To prove. So for any X in the group G, then we want to show like here, this one H, we want to show that F1G should be equal to this one H. This is what we want to show. So for any X in the group G, then X times 1G, then we map it to H, we will get, according to the property of homomorphism, we will get Fx times F1G, right? So this is following the property of the homomorphism. On the other hand, the left-hand side is also equals to Fx, because 1G is the identity in the group G, and X is an element of the group G. So this is equal to equal to X. So this left-hand side is equal to Fx. And then we can say that we can get Fx F1G is equal to Fx. So this is true for any X in G, and also Fx is any element in the group H. So this F1G is right identity of the group H. Similarly, if we consider fx times like this, if we consider f1g times fx is an element of H, and according to the property of homomorphism, we get f1g times x, and this is x, we get fx, so we get this fx is equal to f1g times fx. So this means f1g is the left identity of this group, and because from those two equations, f1g is both the right hand side identity and the left hand side identity of the group H, then f1g is the identity. In H, and because the identity in H is just one H, so we get what we want here, this one. Okay, so this just shows that then the identity in G is mapped to the identity in H, and this is a very important property for homomorphism. Okay, and I think that's all I want to talk in this episode. Thank you for watching, and see you next time. Bye.